It's almost. Do we wait?
Sure.
Just a minute. Okay. Maybe we'll wait for one more minute.
Yeah.
There's only 12. Start. Okay, welcome everyone to the second sessions of this afternoon. Our next speaker is Professor Srikanth Iyer from ISC. His research interest is in stochastic geometry, mathematical finance, interactive particle systems, and many others. And he is going to talk on phase transitions and percolations at criticality in some random graph models on the plane. Srikanth, over to you.
Thanks, Anup, and thanks also to all the organizers for organizing this workshop. So this is the topic of my talk, and it's joint work with Sanjay Jhawar, who was a PhD student here till recently. So the topic is on percolation in. So what is the percolation problem? Percolation refers to the existence of an infinite component or a giant component in a graph. The graph is large and finite. And the interest is in what is called as phase transition. So phase transition means that there is an abrupt, as the parameter governing the graph varies, there is an abrupt emergence of some interesting phenomena. And the interesting phenomena that we are interested in is the transition from non-percolation to percolation in certain geometric random graphs. That is, the graphs will have vertices in space, and there will be certain rule to connect vertices with edges, and these graphs are on the plane, that is in R2. And if such a phase transition occurs, the second question that we ask is, what happens is the percolation function continuous? That is, does percolation occur at the critical point? And what is special about the plane? In a plane, what happens is that if you have paths so if you take a box and you have a path going from left to right and a path going from top to bottom, then these two paths must intersect. And this is a very important and useful property, and it makes a big difference. For example, if one looks at the square lattice and looks at the nearest neighbor Bernoulli percolation model, independently placing edges between vertices in Z2 with probability P, then it is known in for dimension 2 that there is no percolation at criticality, whereas the problem is open, for example, in dimensions 3 up to, I think, 10. Right? So the plane has some very nice structure, which one can actually exploit to say something more. So what is the first model that we will consider? It's called the Poisson Stick Model. It's also known as Poisson soup of sticks. The vertices of our graph will be a homogeneous Poisson point process in R2 with intensity lambda. It's denoted by the script P sub lambda. What this means is that if you take any nice Borel set in R2, then the number of points will be distributed according to a Poisson distribution with the mean equal to lambda times the Lebesgue measure of that set. And if you take two disjoint regions in space, then the number of points are independent. The second ingredient in the model is a probability density function with support in 0 infinity. And what we do is at every point of P lambda, we place a stick whose midpoint is placed at the points of my Poisson point process, and the lengths of the sticks are distributed according to this distribution. The half length of the stick is given by this distribution H. And the orientation of the stick is random, and the distribution of the orientation can be arbitrary. It just should not be degenerate. And what we have is, one can think about this graph as follows. You have these sticks, and intersecting sticks form a path in the graph. Okay, so just to illustrate. So this is not a very nice illustration of points in a Poisson point process, but if we assume that x1, x2, and so on are points of my Poisson point process, and there is, let's say, a point at the origin, then these are the sticks that are placed at these points, and you can see that these intersecting sticks will form a path in the process. You can think of it as a graph. For example, x1, the neighbors of x1 here are the origin and x2, but it's more, it's better to think in terms of these sticks, and that you can actually walk along these sticks and go. The question is, how far can you go starting from the origin? And this model was introduced quite some time back, in way back in 1991 by Rahul Roy. And he considered this model where this half-length density has bounded support. So the sticks have random lengths, but they they're all, the lengths are bounded. And while talking to some people from nanoscience, it looked like, so they refer to this kind of models being looked at by, not quite models, but they seem to be natural models for materials where you have this very thin wires that are embedded in that material. And when two of these wires intersect, you can think of current passing through them. And they study the conductance and other properties of these materials. So there is some nice literature on this thing, but there's no mathematical modeling asset, but this seems like something that may fit there. And there are a few other places where people have also done some statistical analysis for such things. And there are some related models that I will refer to a little bit later as well. There are what are called as scale invariant spatial networks, and where you see similar objects appearing. For instance, what is called as a Poisson line process. So at every one of these points, you place a bi-infinite line passing through that point of the Poisson point process with arbitrary orientation. So while we are at it, we can actually throw in a couple of other models. I don't want to get into the thing of how we came to these, considering these models and so on. So the first model is what is called as a random connection model. This again was introduced by Matthew Penrose in 1991. And again, the vertex set of this model is a Poisson point process. And we have a function called the connection function G, which maps 0 infinity to 0 1. And there is an edge between any two nodes located at x and y with this probability, and independent of everything else. And this model can be shown to be trivial if and only if this integral here is strictly positive and finite. So one can actually show that the degree distribution of any vertex is going to be Poisson with this mean. And so if this is infinite or 0, then you would have a trivial model, right? And in considering these kind of networks, there was a very nice model that was introduced on the lattice, ZD lattice, by these three authors in 2013. And this is what we call as the inhomogeneous random connection model. And in this, what happens is the vertex set is again your Poisson point process. And at every vertex, you assign a certain weight. Let's call it W sub x is the weight at vertex x. And the vertex weights are having this Pareto distribution. The weights are always greater than 1. And they have this kind of heavy tail distribution. And there are two parameters which are important here. One is alpha and the other is beta. And one can see that if the weights are large, then there are a lot more edges emanating from that vertex. If alpha is large, then you would have shorter edges. And if beta is small, you would have this weights having a lot of fluctuation. There would be like vertices with very large weights. For example, if beta is less than 2, then you would have infinite variance of these weights. Right? Beta is less than 1, then you would have, you won't even have finite mean. So you would see like some vertices having very large weight, and so they will attract a lot of edges. And this model was shown to be non-trivial if and only if the minimum of alpha and alpha beta is larger than D. Now, this model was studied in great detail by Deprez, Hazra, and Wuthrich, and they showed that a very large number of interesting properties that are seen in real-life networks can be realized on this graph by tuning these parameters appropriately. And what we do is we consider these two models, the random connection model and the inhomogeneous random connection model, and we enhance these models. What we mean by that is the following. We think of edges as line segments, and when two line segments intersect, we create a junction there, right? So we enhance this graph in this way. So to put it in another way, you think of these edges as line segments, and a path in my graph would be contained entirely in some union of edges, where each subsequent one overlaps with the previous one, right? So an illustration is given here. So this green marked this thing is a path, and so you have a path in this enhanced graph going from the left of this rectangle to the right side of this rectangle, whereas this will not be a path in my original graph, right? So the original graph will have only a path something like this, or these these edges, or maybe this one as well. Okay. So we do create extra edges, and you can see that this model would make sense only in 2 dimensions. And there are some other related models that have been looked at in literature. I will not spend too much time on this. The reason I'm putting this up is because there are some,
a small quick question. So when you put this line, do you maintain some kind of angle with horizontal lines, or I mean, how do you put this line?
The endpoints of these lines are the points of my Poisson point process.
Oh, okay.
So if this is the point X and this is Y, the probability that this line, this edge will exist will be given by this function G. In my random connection model, it will be given by this function in the inhomogeneous model. So for example, if this is a vertex and this is a vertex, there will be a weight Wx here and Wy here, right? Yeah. And so this the presence of an edge will be given by this probability. Okay. So you can see that if your weights are very large, then the probability will be larger. And if alpha is large, the probability will go down for everything else being fixed. And if beta goes down, then you will see that there will be lots of weights, very large weights that you will see. Okay. So, but the thing that you see here is that the weight of this vertex here will influence whether this edge exists and this edge exists, right? So that's common to both these guys. Whereas if I look at this edge, that the presence of this edge will be independent of these two guys, this presence of this edge, right? So there are some additional dependencies that get created when you have this enhanced model. Okay. Of course, this dependency is there in the original model as well. I hope I answered your question.
That's fine.
Yeah. So the questions that are asked in this, so there is a whole bunch of spatial networks that were introduced and studied by Aldous and co-authors. I mean, so Aldous remarks that they are not quite spatial networks because the dimension they consider is only 2, which is what we have. And they are not quite planar networks because they don't create a junction when these edges between these when these edges kind of cross each other. But in our case, we do create this. I mean, you can think of creating these additional vertices here, right? So in some sense. All right. So these, if you go back to the original motivation for this percolation models, you can, as fluid flow in a porous medium, you can think of these as road or pipe abstractions of road or pipeline networks where traffic or fluid can switch from one edge to the other. And one can ask similar questions to the one that were asked in this paper matters, like route efficiency, things of that nature. There are some interesting statistics there. We didn't look at those, so I'll not say more about that. So just to come to the first result, quickly recall that when we had these three models, the Poisson stick model had a half length of the sticks given by this probability density function H. In the random connection model, we had this connection probability function G. And in the inhomogeneous random connection model, the connection probability was given by this formula here. Okay, and then we enhanced these two models. And the first result is on phase transition. So when we say the phase transition occurs in lambda, what we mean is that there is a non-trivial value lambda c, which is strictly positive and finite, such that for all lambda less than lambda c, all components are finite. For lambda greater than lambda c, there is a unique infinite component in the graph. And the condition under which we could show that a phase transition occurs is that this third moment of G is finite. In blue, what we have here is the condition for the original model. For the random connection model, you only require that the integral of G is finite. And in this case, as I just mentioned, that this is necessary and sufficient. Now one can see that if the random connection model percolates, then the enhanced model also percolates, right? So this condition is enough to show that for large enough lambda, that is for lambda larger than the critical probability for the random connection model, you will have percolation. However, in order to show that lambda is non-trivial, that is, lambda c is strictly positive, that is for sufficiently small lambda, you won't have an infinite component. We seem to require this condition, even though we can't say that if this is not met, that there would still be non-trivial. Okay, so it's only one way we are here for the lower bound. For the inhomogeneous model, this was the condition that is required. If you recall, the condition for the model to be non-trivial was that the minimum of alpha and alpha beta should be greater than 2. And so alpha beta is required to be greater than 4 in order for the model to have a non-trivial phase transition. So if alpha beta is between 2 and 4, then what happens is that lambda c becomes 0. So for any small positive lambda, you will have an infinite component in the graph. And whereas what we need here is that alpha beta has to be greater than 8 and alpha greater than 4. So it does look like the enhancement substantially increases the number of edges that are formed. And it is quite likely that when these conditions are not met, you would have a trivial value of lambda c equal to 0. That's what we expect, but we have not proved it. And so it would be interesting to actually show that the lambda c for the enhanced model is strictly less than the critical probability for the non-enhanced model. And for the Poisson stick model, Rahul had proved this result for this H having bounded support, and what the condition we need is that H has finite second moment. So now we come to the second result. This is called as the RSW lemma in percolation. So these RSW lemmas are peculiar to 2 dimensions, and they are the kind of key ingredient in making a lot of results proofs work in 2 dimension. And what it says is something very simple. It says that if your probability of crossing squares of side lengths at least 1, so you look at all squares of side length at least 1, and the probability of getting a path from the left to the right is uniformly bounded away from 0, then so is the probability of crossing a rectangle along the longer side. Okay, so it seems like something that should be true, but it's not always. It's quite non-trivial to prove this kind of result, and this once you have a crossing in the of a rectangle, then what it allows you to do is to piece together paths, as I will illustrate shortly, and build much longer paths and circuits and so on, which allow you to do the analysis. And one of the things that one uses is to show the continuity of the percolation function. There are various critical intensities that one can define in a percolation model. You can this RSW lemmas are used to show that those critical intensities are same. There is this area of noise sensitivity where if at criticality you perturb the model a little bit, so you resample each of these points in a certain way, and let's say you thin your Poisson point process by some epsilon, or do some epsilon thinning, and then you add some epsilon, another Poisson point process with epsilon many nodes. The question is, does the behavior change dramatically, right? And in such cases, one needs to show that the behavior of this crossing probabilities is bounded away, is non-trivial, is bounded away from 0 and 1. So there again, this kind of result becomes very useful. So this RSW lemma was proved for Bernoulli, independent Bernoulli bond percolation way back in 78. And then in the continuum for the what is called as the Poisson Boolean model, this is a model where you have a Poisson point process and you place balls around each point of some random radius. And when the radii are bounded, then Rahul Roy, I think in his thesis, showed this RSW lemma. And this is a highly non-trivial extension from the lattice to the continuum. And this was where the situation was until 2016, when Tassion actually proved this for in the unbounded case. So for the Poisson-Voronoi percolation, the Poisson-Voronoi percolation is one where you have a tessellation of the plane into cells such that each point, so each cell is associated with one point of the point process, and all points in the cell have that point of the Poisson point process as the closest point. And this is quite an astonishing proof. Later this was also proved for this Poisson Boolean model under some moment condition, unbounded radii. Here they require a much more general version of the RSW lemma. And that was used to prove non-percolation at criticality, along with sharpness of the phase transition. So it turns out that so what we want to show is that if the probability of crossing a square is bounded away from 0 or converges to 1, then the same thing happens when you have a rectangle of with a certain aspect ratio rho. It turns out that it's sufficient to prove the result only when the aspect ratio is 2. So you can, like I said, I mean, once you have this result for 2, you can piece together paths in this way. So you can tile this rectangle with the aspect ratio rho by this with a finite number of rectangles of side length with aspect ratio 2. And then you already have with a high probability or with a non-trivial probability a crossing from top to bottom. And so you get, so that's what I meant by RSW allowing you to do interesting stuff. Okay? And this makes sense only in 2 dimensions. And so here is the main RSW result that we have. So in this case, we assume that our connection probability for the random connection model decays like R to the minus C, and with C greater than 4. And in the inhomogeneous model, we assume that the minimum of these 2 parameters is greater than 4. And for the Poisson stick model, we need the half length to decay like L to the minus C with C greater than 3. And under this condition, what we can show is that if the probability of crossing a square of side length S is uniformly bounded away from 0, then for any rho, it happens for a rectangle with aspect ratio rho. So the longer direction is rho times S, and the shorter this thing is S, right? And the same thing is true if this goes to 1, then this also goes to 1. And using that, one can show that the percolation function is continuous by a renormalization argument. Now, in this Hazra's paper, which was then extended to the continuum by Deprez and Woothridge, they show for the inhomogeneous random connection model by a completely different technique that the percolation function is continuous under this condition. Of course, that technique works for all dimension. I've just written the result for dimension 2 here. So now you can see that we did try to extend this result when alpha beta was between 2 and 4, and we could not succeed. But we didn't look at whether this technique would actually work in dimension 2, in which case we would have have extended this result even when alpha is between 2 and 4. So that remains to be seen whether we can actually use the technique here, which is completely different, doesn't use the RSW or anything. It works for all dimensions. And the ingredient of the proof in the last 5-6 minutes, I'll just say a little bit about the ingredients of the proof. It's quite astonishing that the ingredients are something very, very simple. You don't need some very hard estimates. The first one is what is called as the FKG inequality. It says that if you have two events which are increasing, so increasing in general would mean that when you add more points to the graph, or when you have more edges or something like that, then the event, if the event occurs for a particular realization and you add more points or more edges, then the event continues to happen. Now, in our case, the events of interest would be like large boxes, and the event would be determined by all the edges that intersect the box. And these edges could be a priori very long. And what we need to do is to prove an FKG inequality that combines the FKG for a finite discrete percolation model and for square integrable functions on a Poisson point process. This was derived by Last and Penrose. And that is one ingredient. Then using this FKG inequality, one can derive something called as a square root trick, which says that if you have a bunch of increasing events AI, then the probability of the maximum, or if they are all equal, the probability of each one of them would exceed this. So what it tells you is that if the probability of this union goes to 1, then so does the probability of the maximum. So if you have a crossing from left to right, which and if this probability goes to 1, then this would tell you that if you break that right hand side into 2 pieces, the probability of hitting one of those 2 will go to 1. If you break it up into, say, 10 pieces, one of those 10 pieces will have probability going to 1. So that's a kind of interesting upshot of this square root trick. And so what you'll do is leverage this FKG, the square root trick, and the invariance, translation, rotation, and reflection. So these are part of the usual this thing. What you need also is to somehow control the correlation decay. You have to see how fast these dependencies decay, and you need to bring that in appropriately. Now, in the Poisson Boolean model, as I mentioned, you don't have this kind of a symmetry that you have in the Poisson-Voronoi percolation, and one needs to prove a stronger version of the RSW lemma, which I will skip what it is. Okay, so this correlation controlling, what happens in the Poisson-Voronoi case is that if you have enough points, if you consider an annulus, and if you have enough points inside the annulus, then these cells don't cross that annulus. Okay, so that's the kind of trick that one uses in order to control the size of these cells. And in the Poisson Boolean model, this is done by looking at 2 plus epsilon moments. What we need to do is to look at the length of the longest edge that intersects a large box. And what one can show is that if the connection function decays in this fashion, and if this parameter C is large, then you can pick a tau positive, which is less than 1, such that the edge of the longest edge that intersects your box B of TS exceeding as tau goes to 0. So that can be very small, and that would be the key ingredient in controlling the correlations. The last this thing about how you then do this show that the percolation function is continuous. What you do is you do a renormalization. You map your percolation model to a discrete bond percolation model. So you look at the lattice 4n times z2, right? And you say that there is an edge between this origin and 4n comma 0 if there is a path going from this box bun, which grows slower than n over 2, and it hits this box, a similar box here. And there are circuits around these 2 boxes, and no edge of very long length actually intersects a box centered at 2 and 0 of side length 4n. Okay, so and in order to show that such a path would exist with high probability, you use a square root trick to say that, look, with a very high probability, there would be some interval here which would be hit by this path. because with very high probability, if un grows, there would be this would hit the infinite component, and then use the square root trick to say that the infinite component would hit this right hand side with high probability, and then some interval here with high probability. And then you build these circuits using the RSW lemma, and then you patch these paths together. And so you end up with a finitely dependent bond percolation model. And then you show that the mapping of the intensity parameter lambda into this bond percolation model is a continuous function. And one uses that to show that the percolation function has to be continuous. So that's one application of the RSW result. Okay, so I'll stop here. Take questions.
Okay, thank you, Srikanth, for wonderful talk. Any questions, comments, suggestions? Okay, now maybe I missed something. So your point-to-point process intensity was lambda, and that's what fixed, right? And
so
all
that,
the
right,
yeah. So all the conditions that you're showing that alpha staying between 2 and 4, and then alpha beta bigger than 4. So somehow lambda doesn't show up in the picture.
No. So when alpha is in those ranges, then for example, if you go to the first result, so when alpha is in this, when the say alpha and beta satisfy this condition, then what you have is you have a critical lambda c,
Okay.
a lambda c, which is strictly positive and finite, such that when lambda is less than lambda c, you don't have any phase transition. When lambda greater than lambda c, you have a phase transition. For example, in this case, if alpha beta was less than 4, for example, then lambda c would be 0. So there is no non-trivial phase transition. So these are conditions under which we show that there is a non-trivial phase transition.
There are no other questions. Let's Srikanth for this talk. So next talk is at 4:10, I guess.